Introduction to quantum entanglement. Entangled particles are particles that have correlated properties or states such as spin, polarization, or momentum.
The entangled particles were created simultaneously and are part of the same wave function.
Their states may be opposite, parallel, or complementary in a specific way.
For spin state, for example, opposite means that one is spin up and the other spin down, and parallel means that both are spin up. Complementary means they share a specific type of relationship.
When particles are entangled, their quantum states are correlated, but undefined until measured or disturbed, an event that causes the wave function to collapse. This connection is preserved even across large distances. What makes entanglement so remarkable is that nothing travels between the particles, yet measuring one instantly reveals the state of the other. Different particles can have various quantum states. Electrons may be spin up or spin down, photons can be polarized vertically or horizontally, and atoms might be in excited or ground energy states. Many particles have more than one such state at the same time. Entanglement can be created, for example, by shining a laser on a crystal to emit two entangled photons, or by using microwave pulses on qubits in a superconducting quantum processor. A measurement collapses the shared wave function and both particles' states are determined. Entanglement is confirmed statistically by performing multiple measurements from different angles. How was entanglement discovered? After quantum physics introduced superposition, physicists realized that two interacting particles remained somehow connected even when far apart. It was found that when one particle was measured, the state of the other one could be predicted. In the 1930s, Einstein, Podolsky, and Rosen claimed that the particles must have local hidden information because particle A can't send its state to particle B when measured, since that would be a faster-than-light transmission. They called this information hidden variables, which must be there from the start. Einstein famously referred to this phenomenon as spooky action at a distance. Niels Bohr and other scientists claimed there were no hidden variables, insisting that the values were undefined until measured. Physicist John Bell proposed a test. If the particles carried information from the start, the results would follow a predictable pattern. Bell calculated the limits of that pattern, known as Bell's inequality.
In the 1970s, John Clauser and Stuart Friedman, along with other scientists, measured entangled photons at different angles. They found violations of Bell's inequality, matching quantum predictions and backing up the non-locality idea. Various additional experiments, like Elan aspects, confirm that quantum particles behave as parts of a single system. It was found that when two detectors, each measuring a different entangled particle, are at different angles, the results correlation follow a cosine curve that is relative to the angle's difference. The entangled particles, therefore, must be part of the same wave function, revealing both their states when it collapses. Quantum computing uses entanglement to perform certain calculations much faster than classical computers. When particles are entangled and placed in superposition, they can represent multiple combinations of values at once, allowing parallel computation across many possible states. This makes quantum computing exponentially more powerful for solving certain problems, driving forward innovation and technology in many fields.